Hybridization theory. Let me put an overview over the hybridization theory explained by this professor. You can see the image. In the image, he looks very funny. Ammonia, according to hybridization, you have its orbitals. According to the quantum number theory, the orbitals are perpendicular 90 degrees according to its shape. Alright, we have this orbital 2 inside the NH3. We have 2 electrons. Upward and downward arrow shows the spin quantum number. Alright, Pg, Px, Py respectively in the P shell. Afterwards, we have a prediction that H and H bond angle should be 90 degrees according to theory. For experimental, you have found out that bond angle is 107 degrees between H, N and NH. We have 107 degrees of angle according to experimental confirmation, but theoretically we said there is 90 degrees or should be 90 degrees according to quantum theory and other theories of bond localization and lone pair bond pair localization. Afterwards, we have quantum mechanics. Electrons occupy orbitals in atoms. Alright. Quantum mechanics generally expresses the idea that electrons, which are negatively charged elementary particles in an atom, will always occupy orbitals or energy levels inside atoms. Alright. What are molecules then? So, molecules, according to hybridization, what will hybridization talk about molecules? That what are these structures like? So hybridization mainly accounts for a difference between atomic orbital orientation and observed molecular shape. So the general idea of hybridization about molecules is the basic difference between atomic orbital orientation and the observed molecular shapes of elements which are taken during atomic orbital orientation and molecular shapes orientation. So according to hybridization, we have central atom with 2 electron regions. You can see in carbon case we have 2 electron regions around carbon, or electron regions that are surrounding carbons, 2 lone pairs. And the concept of orbital, we have Pg, Px, Py and s orbital that will hybridize and respectively will form Px, Py. Alright, and the Pg will combine, or a Pg orbital or a Pg electron cloud, or electrons will combine with this and will form 2 sps, or will form 1 sp and another sp. And the situation arises likewise that the atomic structure of carbon dioxide will be likewise. You can see in the diagrammatic representation here we have Px, Py, alright, respectively. Then we have the sp being in here, and we have the lone pair, this one and that one, respectively to the oxygen of the carbon dioxide. Now according to central atom with 2 electron regions, we have 1s orbital combined with 1p orbital, making 2 sp orbitals, 1 sp and second sp being combined in here in the equation, and the circle position of the written form of central atom with 2 electrons will express that we will have 50% s character and 50% p character being combined and form 2 sp orbitals with an angle of 180 degree. Alright, hybridization will happen likewise that s, Pg, Px and Py, 1 sp will combine with another sp being in here. You can see 1 sp, second sp, and the hybrid orbitals will be used for sigma bonds formation and lone pairs. Hybrid orbitals are used for generally for 2 purposes: sigma bonds formation and lone pairs. So what's the main concept of hybridization we discussed earlier? Atomic orbitals and molecular orbital difference accounting is a general hybridization job. So hybrid orbitals are used for sigma bonds lone pairs, which are molecular characteristics, and in here we have atomic orbitals. So pure orbitals are used for 5 bonds formation, and the angle will be 180 degrees. According to hybridization theory, we have certain examples of, let's say, ethylene, which is C triple bonded C, and single bonded hydrogen. Formula will be C2H2 having 2 carbons, 2 hydrogens, 2 hydrogen being singly bonded form 2 sigma bonds with each carbon respectively, and each carbon had formed 3 bonds with each other, in which 2 are pi. Let's say the upper 2's are pi and the lower one is sigma. Hybridization theory, another general example, includes the nitrogen gas generally, in which we have 2 lone pairs, one on the right, one on the left, and 2 pi bonds on the upper portion and 1 sigma bond on the lower portion. In hybridization theory, general other example which we expresses already is the carbon dioxide being produced from chimneys in industrial applications. If, let's say, lime is prepared from lime water, so we have calcium carbonate being treated with certain metals at certain conditions of temperature or desired conditions, and we have calcium oxide and carbon dioxide being formed. So the carbon dioxide generally shows hybridization phenomena in its orals. Let us talk about generally about sp2 hybridization, in which we have a central atom, let's say carbon oxygen fluoride molecule, which is a derived molecule I know, having double bonds with oxygen, no carbonyl carbon, and H is a belonging component of ketone group, and the F has just replaced the methyl group, or let's say the alkyl group, respectively from each ketone compound. So hybridization is central atom with 3 electron regions will hybridize in such a way that the 1s will combine with Pg and Px, and Py will remain alone, which is a pure p orbital, and they will hybridize in such a way that 33% as character will participate and 66% of p character of the orbital will participate in combination of atomic orbitals.